ma'am, about the announcement, ma'am.
Yeah,
Is the problem if we write on Saturday? Uh, give us time to prepare.
most people do not want to write on Saturday. They are saying they have problems or something. They would rather write tomorrow than on Saturday.
Okay.
Okay, so we continue with eigenvalues and eigenvectors. So like I said, with us, all we are doing is simply working out the eigenvalue. So like with this one, we got our eigenvalue as 6, and then we find the eigenvector associated with that eigenvalue. Okay, so there isn't just one eigenvector, there is a way that they look. So with this one, when our eigenvalue was 6, we said any column matrix that looks like this, A will be an eigenvector, and this one we call it the usual eigenvector, where we let A equal to 1. So we have 1 1, you can make it 5 5, 10 10, and so on, and you will see that any column matrix of this form will satisfy this equation. So I hope you got the associated the associated eigenvector when lambda is equal to 1. Today we look at another example. Number 2. We have a matrix A. It is 4, 2, minus 2. Then 1, 3, 1, minus 1, minus 1, and then 5. Okay, so we want to determine the eigenvalues and the eigenvectors of this matrix A. So remember, we need the characteristic equation A minus lambda I is equal to 0. That is, the determinant of this matrix must be equal to 0. And then this matrix here, A minus lambda I, looks like this. It's 4 minus lambda, 2 minus 2, 1, 3 minus lambda, 1, minus 1, minus 1, and then 5 minus lambda. So you subtract lambda on the leading diagonal, and then you work out the determinant of this matrix. So the determinant of A minus lambda I. So remember how we do it with the cofactors. This term here is positive, negative, positive, negative, positive, negative, positive, negative, positive. And working out the determinant, you can go along any row or any column as long as you keep these signs in mind. So we'll go along the first row. So our determinant will be this positive of this term, which is just 4 minus lambda, and then we remove the row that the term we took is in and the column that the term we took is in, and then you look at the matrix that is left. So you'll be left with this matrix here, and then work out the determinant of that matrix. So the determinant of that matrix is just this, the product of that minus that. So we will have 3 minus lambda, 5 minus lambda, and then minus negative 1 times 1. which is equal to +1. Okay, then we move on to the second entry in the row, and this one has a negative. So we have -2 multiplied by, we remove the row that it is in and the column that it is in. You can see the matrix we're left with is this one, that one, that one, and that one. And then we work out the determinant of the matrix that we're left with. So it's like we remove like that, then diagonal minus that diagonal. This gives us 1 times 5 minus lambda, which is just 5 minus lambda, and then minus -1 times 1. So it's minus -1, which is +1. And then the last term here, it's a positive -2, which is just -2. And then again, you remove the row and the column that -2 is in, and then work out the determinant of this matrix that we're left with here. So that's 1 times -1, which is -1, then minus -1 times 3 minus lambda. So minus negative will give me positive 3 plus lambda. Okay, and remember, this determinant must be equal to 0. Okay, so now we have an equation that we can solve for lambda. So you can multiply out your brackets, simplify however you do it. The way you actually solve it is really up to you. So let's see, what do we have? 4 minus lambda, 3 minus lambda, 5 minus lambda. Then we have plus 4 minus lambda. Okay, so I've multiplied this one out there. Then this one here, we have -2 times that. So I have -2, 5 minus lambda, and then -2 times 1. This is -2. Then -2 times -1. This is +2. So you can see those two will cancel. And then -2 times 3 minus lambda. So -3 and then 2. Sorry, not -3. It is -2. 3 minus lambda. This is equal to 0. So we see that these two will cancel. Okay, then we can expand this. This is 4 minus lambda minus 10 plus 2 lambda minus 6 plus lambda. So I have 4 minus 10 here. Okay, so I have 4 minus 10 when I multiply that out, and then minus 6, which is -12. So this one here, I'll leave it the way it is for now. I have 4 minus lambda, 3 minus lambda, 5 minus lambda. Then we say we have minus 12. Then look at all our lambdas. I have minus lambda here, and then plus 2 lambda, and then plus 2 lambda. This gives me 3 lambda. This is equal to 0. Then here I can factor out 3 or negative 3. So I have 4 minus lambda, 3 minus lambda, 5 minus lambda, and then minus 3. I have 4 minus lambda. This is equal to 0. So you can see that 4 minus lambda is a common factor, so I can also take that out. So I have 4 minus lambda and 3 minus lambda, 5 minus lambda, minus 3. This is equal to 0. Then we can multiply this out, get 4 minus lambda. And then we have 3 times 5 is 15. 15 minus 3 is 12. Then 3 times minus 1. 3 times minus 1. And then minus 1 times 5. This gives us minus 8 lambda. And then minus lambda times lambda, this is just lambda squared. 0. Okay. Then this is quadratic. You can factorize it, look for 2 numbers. When we multiply them, the answer is 12. And when we add them, the answer is minus 8. That is minus 6 and minus 2. So I have 4 minus lambda. And then here I will have lambda and minus 6 minus 2. Now I can solve it. So 4 minus lambda is 0. This means lambda is equal to 4. Lambda minus 6 is equal to 0. This means lambda is equal to 6. Lambda minus 2 is equal to 0. 0. This means lambda is equal to 2. Okay, so now we have our 3 eigenvalues. We need to work out the eigenvectors associated with each of them. So we start with lambda is equal to 4. So what we will do is we will substitute 4 into this matrix here. So we'll have 4 minus 4, 3 minus 4, and then 5 minus 4. That is our A minus lambda, our characteristic matrix. And then we will multiply that by x1, x2, x3, and equate it to 0, 0, 0. Okay, so what we have is this. We said 4 minus 4 is 0. Everything else in the row stays the same. And then we have 0, minus 1, 1, minus 1, minus 1, 1, x1, x2, x3. This is 0, 0, 0. So this matrix here, this is the eigenvector that we are trying to work out. So we need to work out the values of x1, x2, and x3. And this is just a system of linear equations that we have worked out. We draw the augmented matrix, which is 0, 2, minus 2, and then we have 0, 1, minus 1, 1, we have 0, minus 1, minus 1, 1, and 0. Okay, and then we want to have the identity matrix over here, and then from there we not necessarily the identity matrix, we want to see how many distinct column vectors we have. Okay, so what we can do here, we can say row 3 plus row 2. Okay, so I want to make this a 0. So if this is a 0, then I already have a column matrix over here. So this will give me 0, 2. I can also divide this one by 2. So it's 1, minus 1, 0. Then 1, minus 1, 1, 0. And row 3 plus row 2 minus 1 plus 1 is 0. Minus 1, minus 1 plus minus 1. Here this should be minus 2. And then 1 plus 1, this is 2. Then 0 plus 0 is just 0. Okay, then I can also divide this by 2 or negative 2. And then I can say, if I want to make a 0 here and a 0 there, so I'm left with a 1 here. So this one, let me say row 2 plus row 1. Okay, that will give me a 0 here. And then maybe instead of dividing by minus 2, I can just go ahead and make a 0 here. I will just say row 3 plus 2 times row 1. Then I'll have a 0 here and a 0 there, which is not what I want, because it won't be different from this one. Okay, let's just do that one. They just divide it by negative 2. Okay, so first row doesn't change, so I have 0, 1, minus 1, then 0. And then we said row 2 plus row 1. So 1 plus 0 is 1. And then minus 1 plus 1, this is 0. And then 1 plus minus 1, that is 0. And then 0 plus 0, this is 0. Then row 3, we've divided it by minus 2, so I have 0, 1, minus 1, and then 0. Okay, so this one here is a column vector that I want. So here I can either make this one a 0 or that one a 0, then it's unique. So it doesn't really matter. So I will make this one here a 0. So I will say row 3 minus row 1.
And,
So this is, yeah.
I just want to know, man, in this case, are we not trying to get to the form of the identity matrix, or we just trying to find uh, unique unit column matrix?
We're trying to find unique column matrices. So we're actually trying to solve for x1, x2, and x3. If we can make an identity here, that's fine, because each of them will be unique, but it's not always the case. In fact, here with eigenvalues, you will probably not get an identity matrix on this side. So what you want is unique column matrices, so that you can say this is my basis, and then the non-basic variables, you make them A, B, or C, like that. 1, 0, 0. Okay, then we said row 3 minus that, so 0 minus 0 is 0. And then here we have 1 minus 1 is 0, minus 1 minus negative 1, and then 0 minus 0. Okay, so that is what we have. And you'll see that it is not possible to change that one without changing this one. So you have only two unique column matrices, the first and the second one, or the first and third one, depending on which one it is you want. Okay, so I like to pick the first two. Okay, but before that, we can see with this second row here, we have x1 0, 0, 0. So this means, if I look at this row here, this means that x1 is equal to 0. So that is definitely the case. x1 is equal to 0, because I can work that out. Then it means that my basis is just made up of either this x2 or x3, because this one is obviously equal to 0. So our basis is x2, and then the non-basic variable is x3. So we let x3 equal to a. Okay, so if x3 is equal to a, we now rewrite x2 in terms of x3 using this equation. X2 minus x3 is equal to 0. If x2 minus a is equal to 0, this means x2 is equal to a. Okay, then our X matrix, which is our eigenvector, will be x1, which is 0, x2 is a, and x3 is a. So this is the family of eigenvectors associated with lambda equal to 4. Okay, and then we have what we call the usual eigenvector. So this one is where we let a equal to 1. So we have 0, 1, 1. And that means it will satisfy this equation, a minus lambda I is equal to lambda x. Okay, so if you put your matrix X, which we started with, what's that? This one here, and then you multiply it, just so we have our matrix A over there, and then you multiply it by this matrix here, 0, 1, 1, like that. This will be the same as 4 multiplied by 0, 1, 1. Okay, and here, as long as you pick any A that is a real number, you can make this 2 and 2, 2 and 2 over there. You will see that it satisfies this equation. And you have to do the same thing for lambda equal to 2. So when lambda is equal to 2, you have your A minus lambda I, and then you write down the augmented matrix. So A minus 2I, so you'll have 4 minus 2, which is 2, then 2, and minus 2, and then 1, 3 minus 2 is 1, 1, and then minus 1, minus 1, then 5 minus 2, which is 3. Okay, so this is A minus lambda I, and then we have the augmented matrix 0, 0, 0, like this. So we are trying to solve for x1, x2, and x3. So here, for the first row, we can just say row 1 minus 2 times row 2, and then row 3, we can say it's row 3 plus row 2. So here we have, it should be plus, oh no, I'm multiplying this row, not that one, so it's minus, yeah. So it'll be 2 minus 2, which is 1, and then 2 minus 2, which is 2 minus 2 is 0. 2 minus 2 is 0. Minus 2 minus 2 is minus 4. Then 0 minus 0 is 0. Then here we have nothing has changed, so it's just 1, 1, 1, 0. And then we add row 3 and row 2, so 1 plus minus 1, 0, 1 plus minus 1, 0, 1 plus 3 is 4, and then we have 0. Okay, we can divide throughout by minus 4. Just divide by minus 4, and this one here we can say row 3 plus row 1. Okay, so we have 0, 0, 1, 0, 1, 1, 1, 0. Then here we'll have 0, 0, 0, 0. Now if I look at this first row over here, I have x3 is equal to 0, so x3 is equal to 0. So the only two vectors that, the only two unknowns or variables that can be part of the basis are x1 and x2. So we can say that our basis is x1, and it doesn't matter if you pick x2 as your basis, okay, because this basis is not unique. What is unique is the number of variables that will be inside the basis. So if I have a basis, mine will have only one variable. Yours may have a different variable, but they will be only one. You cannot have a situation where I have one variable in my basis and then somebody else has two in their basis. It's not possible. So again, these are the same because the position of the ones are the same. So that is why you can pick either of them. And then you let x2 equal to b. So I'm only picking b because the first, yeah.
Won't the basis be x1 and x3? Because if you say row 2 minus row 1, you'll get that in row x3 that it would be 1 0 0.
If you say row, which row are you working at?
Row 2 minus row 1.
Row 2 minus row 1, and that becomes row 2. Okay, the x3 is not in the basis because from here I can clearly see that x3 is 0. So our basis does not have 0 variables. So we are putting non-zero variables into our basis, not 0 basis. But here, just even when I got to this point, I can see that x3 is equal to 0 because I have negative 4x3 is equal to 0. If I were to solve that, I would have x3 is equal to 0. And even this one here, if I were to solve this, I have 4x3 is equal to 0. Clearly, x3 is equal to 0. So in our basis, we don't put any 0 variables. Only the non-zero variables go in our basis. Okay, then again, the reason I picked B here is because with the first eigenvector, with the first eigenvalue, I used A, so this time I just want to use a different one. Then what I need to do is rewrite x1 in terms of x2. So I have x1 plus x2 plus x3 is equal to 0. So we have x1 plus x2 plus x3 is 0. So this is x1 plus b plus 0. This is equal to 0. So this means that x1 is equal to minus b. Okay, so then our family of eigenvectors will look like this. I have minus b, b, and 0. And then the usual. So with the usual eigenvector, we just say b is equal to 1. So our eigenvector will be minus 1, 1, and 0. Okay, then the last one is when lambda is equal to 6. What we will have is this one here, minus 2, 2, minus 2, 0, 1, minus 3, 1, 0, minus 1, minus 1, minus 1, 0. So again, we want to get as many unique column vectors as possible. So we can start with the first one. We divide it by -2. With the second one, we can say row 2 plus row 3. And then the last one, we will divide it by -1. Okay, so this will give us 1, -1, 1, 0. Then row 2 plus row 3, this is 0, -4, 0, 0. And then divide everything by -1. I have 1, 1, 1, 0. And from here, you can see the other variables x1, they don't contribute. I just have -4 x2 is equal to 0. So that already tells me that x2 is equal to 0. So if I look at what I have over here, so I have -4 x2 is equal to 0. So clearly x2 is equal to 0. So it's not going to be part of my bases. So what I want now is to make this one here a 0. So this is something to take note of. So I can say row 3 minus row 1. And then this second row also just divided by 4, by -4. Okay, so I have 1, -1, 1, 0. I have 0, 1, 0, 0. Then row 3 minus this one, so it's 1 minus 1, which is 0. 1 minus -1, which is 2. And then 1 minus 1 is 0. And then this is 0 as well. Okay. Then from here, even if I make a 0 here and a 0 over there, this will not be, or this column matrix here will not count as a unique column matrix because our x2 here is 0 and it cannot be part of the bases. So here I can tell that my bases is made up of either x1 or x2. So I like to pick the first one, and then we let x3 equal to c, which is a real number. Okay, then our family of eigenvectors. So we use this equation. We have x, let me just do it here. So we have x1 minus x2 plus x3. This is equal to 0. So we have x1, x2, remember, is 0. So it's x1 minus 0 plus x3, which is c. This is 0. And this means that x1 is equal to minus c. So our family of eigenvectors is minus c, x2 is 0, and then c, and then the usual one where c is equal to 1 looks like this, -1, 0, 1. like that. We can do one more. 2, 1. Two, 2, 1, 1, 3, 1, 1, 2, 2. And again, we want the eigenvalues and the associated eigenvectors. Okay, so we will have this matrix here: 2 minus lambda, 2, 1, 1, 3 minus lambda, 1, 1, 2, and then 2 minus lambda. This is our A minus lambda I. Okay, then we work out its determinant and equate that determinant to 0. So we have 2 minus lambda multiplied by 3 minus lambda, 2 minus lambda, minus 2. Okay, so remove this one and that one, then the determinant of this matrix here. Then the next one, this 2 here is negative because the signs are plus, minus, and so on. So we have minus 2. Remove this row and that column. So we have 1 minus that. This is 2 minus lambda. Minus 1. And then the last one, remove this row and that column. So we have a positive 1. So this is just plus 2 minus 1 times that. So that's 3 minus lambda. And this is equal to 0. So this one we have to solve. So we can see that trying to solve it the way we did the other one, we have 2 minus lambda squared, and we have 3 minus lambda, minus 2, 2 minus lambda, minus 2, 2 minus lambda, plus 2. So I'm multiplying this times this pair, then this times that one. And then here I can just remove the brackets. So I will have 1 minus 1 plus lambda, minus 1 plus lambda. And this is equal to 0. Okay, so this is, okay, I can combine these two. This is minus 4, 2 minus lambda. And then this is 1 plus lambda, or just add everything. Anyway, we have 2 minus lambda. So this is just a cubic equation. We know how to solve this. So I have minus 4. See, we have minus 4, minus 4, plus 2 minus 1. This is minus 7. And then positive 2 lambda, positive 2 lambda, and lambda. This gives me 5 lambda. Okay, so there isn't anything we can do to factorize, so we just multiply. This is 4 minus 4 lambda plus lambda squared, 3 minus lambda minus 7 plus 5 lambda is equal to 0. Then multiply everything out. We get minus, or what I got, minus 3 lambda minus lambda cubed plus 7 lambda squared minus 16 lambda plus 12 minus 7 plus 5 lambda is equal to 0. And then this gives us lambda cubed minus 7 lambda squared plus 11 lambda minus 5 is equal to 0. Then we can factorize this. We get lambda minus 1 squared. Lambda minus 5 is equal to 0. So lambda is 1 or lambda is 5. So those are my two eigenvalues. Then the eigenvectors associated with that, here we have 1, 2, 1, 1, 2, 1, and then 1, 2, 1. So you can see that all the rows are the same, so I can make the second one 0. So this is R2 minus R1. This is R3 minus R1. And then this gives us 1, 2, 1, 0. Then the others are just 0, 0, 0, 0, 0, 0, 0, 0. Now, if I look at this, it's not obvious that any of them is equal to 0. Okay, so I can't say for sure that one of them is equal to 0. So if I have x plus 2y plus z is equal to 0, I don't know for sure that one of them is equal to 0. So I have these unit column matrices, but the position of the ones, because I can make this 2, 1 by dividing everything by 2. So I have these column matrices, so my basis can be any one of them, and it doesn't matter which one you pick. So I like to pick the first one. So the basis is x1, and then we let x2 equal to a, and then x3 equal to b. And then we write x1 in terms of a and b. So I have x1 plus 2a plus b is equal to 0. So this means that x1 is equal to minus 2a plus b. Okay, so my eigenvector associated with this one will look like this. So the family of eigenvectors will look like this: minus 2a minus b, and then here I have a and then b over there. And then the usual one, this is where a and b are both equal to 1. So this one will look like minus 2 minus 1. This is minus 3, 1, 1. That's it. And then with the other one, when lambda is equal to 5, the matrix that we have is minus 3, 2, 1. then 1 minus 2 1 0 1 2 minus 3 and 0 here. So I can say row 2 minus row 1 and then row 3 plus 3 times row 1. Sorry, not this. So this one is row 1 plus 3 times row 3. Okay, so negative 3 plus 3 will give me 0. And then 2 plus 6, this will give me 8. 1 plus negative 9, that will give me negative 8. And then I have 0 here. Then row 2 minus row 1. I think I meant to say row 3 here. 1 minus 1 is 0. Minus 2 minus 2 is minus 4. Then 1 minus negative 3 is 4. Then 0 minus 0 is just 0. Then the last one is just 1, 2, minus 3, and 0. Okay, so I can make this one here as 0. So I say row 1 plus 2 times row 2. Okay, so I have 0 plus 0, which is 0, and then 8 plus negative 8 is 0. Negative 8 plus 8, that is 0, and then this is 0. Then this one I can divide it by negative 4, so I have 0, 1, minus 1, 0, and then the last one I don't change it at all. Okay, so I can make this one here as 0, and I just say row 3 minus 2 times row 1, 2 times row 3 minus 2 times row 2. So I have 0, 0, 0, then 0 here, then I have 0, 1, minus 1, 0, then I have 1 minus 0, this is 1, 2 minus 2 is 0, minus 3 minus negative 2, that's negative 1, and then I have 0 over here. Okay, so that is what I have. If I were to try and make this one here a 0, it would change this 0 over here. Oh, let me see if I would say this row 2 minus that one. The 1 minus 0 is 1, and then this minus that is 0. Oh, okay, no, I see why. Right, so if I were to try and make this one a 0, let's say I say row 2 minus row 3, I'd have 0 minus 1, which gives me minus 1. So there's no way for me to make this one here a 0 without changing that one. So this is where I would stop and then say that I have two column matrices that are unique. So I can then say my basis is x1 and x2. So those are the unique ones that I have. And again, it's not obvious that any of them is equal to 0. So I don't know for sure that x1, x2, or x3 is 0, because here I have x2 minus x3 is 0. Doesn't necessarily mean that any of them is 0. Here I have x1 minus x3 is 0. I can't tell that one of them is 0 right away. So that's my basis. So then x3 is equal to a, which is a real number, and then I write x2 in terms of a. So I have x2 minus a is equal to 0. So this means x2 is equal to a. And then I have x1 minus a. This means that x1 is also equal to a. So my family of eigenvectors, this will be a, and then the usual one when a is equal to 1 will be 1, 1, 1. Yeah. Okay, so we'll stop here for today. So I think for now, test is tomorrow at 12:30. It should be pretty much the same, 90 minutes or less. I think it'll still be an open book since the other one was also an open book test. But that doesn't mean you shouldn't study for it. Okay, so we'll continue next time.